All right, so hopefully the quiz was decent. I'll have those graded by the end of the day. And so hopefully you had a good idea as far as how to do those calculations. That's the biggest thing, calculating that percent yield and stuff. So on, what's today? Today is Thursday, so Monday, but on Tuesday, I know that y'all intently watched the video for Tuesday, okay? And at the very end of the class, we're talking about the three solution processes, right? What are they? Three things have to happen for something to dissolve.
The solute has to like break apart.
Okay, so 3 steps, and you already have all this, so this is just review. 3 steps of the solution process. Okay, number 1, solute, solute. Okay, and in an ionic compound, what do we call the energy that we have to put in to break those apart? The lattice energy. Okay, now it's an ionic bond holding them together. Okay, so the type of bond is an ionic bond, but the energy that you have to put in to break that bond is called the lattice energy. And lattice, again, always means orderly arrangement. So you'll hear the term crystal lattice structure a lot. That just simply means the atoms or ions are arranged in an orderly pattern. So the lattice energy is how much energy does it take to break that pattern apart. Okay? Is that going to be, is this going to require energy or give off energy? Require. Breaking up is always hard to do. Okay? It's always hard to do. So this is going to be what we say is a positive delta H, and we call that delta H1. So positive indicates endothermic. H represents heat. The technical term for H is enthalpy. It's a Latin term, and it simply means the energy transfer at a constant pressure. We do most everything in an open beaker. We assume the pressure is constant. So if we really want to get technical, and I'm just sharing this, you don't really have to know this or understand this, but the total energy that you put into something is equal to the heat transfer plus any work that is done. Okay? So the total energy is how much energy is there transferred, but some of the energy gets used as work. Like a gas has to expand, it does work to have to expand. But for most reactions, the amount of work is very minimal. Therefore, we say that the change in energy and the change in heat enthalpy are basically the same. So we're calculating delta H as is if the total energy. Okay? Nutshell what I just said. Energy and heat for our practical purposes are going to be the same thing. Okay? Because the amount of work that's being done is minimal. So I can use the word energy, I can use the word heat, I can use the word enthalpy, and they all kind of mean the same thing. Okay? So, in a covalent compound, what bonds have to be broken? The IMFs. Okay? And so, what are the 3 IMFs? London, which we're always going to abbreviate LDFs, London dispersion forces. Okay, now you can just say London forces, but you can also just say LDFs on any answer. And what type of molecules have LDFs? All. Okay. Which type of molecule is this the only type of attractive force? Non-polar. Okay. So London and with what makes this stronger? The more electrons in the electron cloud. And the practical way of doing that is bigger molecules. Okay, if we look at the molar mass, obviously our potassium trisoxylotoferrate 3-trihydrate going to have a lot of electrons in it. Okay, it's a very big, complicated molecule. Okay, so the London forces there are going to be much stronger, than something like hydrogen gas. So when you look up here on the periodic table, helium only has 2 electrons, therefore, and it's nonpolar. So the only type of attractive force are first off, London forces are the weakest of all forces, and then having only 2 electrons, it's going to be the weakest of all the London forces. Therefore, you have to get helium down to 4 Kelvin, 4 degrees above absolute zero, before the molecules are moving slow enough for them to stick together and for them to liquefy. Okay? So, I mean, very weak attractive forces. It only takes that itty bitty little bit of energy to break them apart. Have y'all heard of the LHC, the Large Hadron Collider, that's in CERN, Switzerland? It's a 23-kilometer underground particle accelerator. And they shoot particles together and try and make new elements, like they're trying to synthesize these. They're trying to find the, I'm having a senior moment here. The God particles. Anybody remember what the name, anybody heard about that?
God particles.
Well, it's this particle or this field that supposedly when E equals mc squared, as energy's going through this field, that's where mass gets attributed to it. And the faster it goes through the field, the less mass it gets, the slower it goes, the more mass it gets. And so it's supposedly the particle that distributes mass. And so they called it the God particle because it's the one making something, okay? I'm going blank as far as I know what the name of the particle is. I'm just, again, because I have to think about it, I can't remember it. It's irrelevant, but the reason I say that is because that LHC is cooled by liquid helium. So they get all the helium, they have to liquefy, which means they have to get it super cold in order to keep it a liquid. So it takes them several months to get the thing cooled down enough to where there's no resistance, so the particles can go, I think they start approaching the speed of light, but because they're little tiny particles. And then if they have to shut it down for maintenance, it takes them again a couple of months just to pump all the hydrogen out, because the helium out, they want to keep track of it because it's expensive. And here's just another trivia thing. Where does helium come from? The sun. The sun has a bunch of helium, but we don't get our balloon, the helium for our balloons from the sun. Okay? But the helium is the number 2 element in the universe, because hydrogen is the number 1. All stars are basically hydrogen gas that's undergoing nuclear fusion, and they're turning into helium. All these fun facts that I have right now that are really totally worthless. Okay? But again, I'm struggling to get the exact number. But it's like 600 million metric tons of hydrogen every second are being converted into helium. Okay? And it's amazing how much, but that just tells how big the stars are, how much gas there is. And they're gonna burn for like 1 million years, So anyway, so the whole point of that diversion is that London forces are the weakest of all, the way we can remember all of these IMFs are way weaker than an ionic or a covalent bond. The hydrogen bond is the strongest one, and in the notes, what did it say as far as the strength?
It's still
For hydrogen bonds, how does it compare to a covalent bond? 1/10, very good. Okay, so, and London forces then are about 1/20th or less of that strength, okay? So, all molecules, and this is again just a review, okay? Only attraction between nonpolar molecules. Therefore, nonpolar molecules tend to be liquids or gases at room temperature because the attractions are very weak, therefore they tend to break apart easily. So at room temperature, there's enough energy to break those London forces. So they're gonna be gases, or they'll be a volatile liquid. What does the word volatile mean there? Volatile liquid.
Explosive.
Well, that's what we normally think of as explosive, okay? But that's not the technical term for volatile. They go hand in hand, but
It's a very reactive.
Sound.
okay? Volatile actually means it goes off quickly. If somebody has a volatile temper, that means that they lose their temper easily. A volatile liquid is one that evaporates quickly, okay? So, if it evaporates quickly, what does that mean about the attractive forces?
They're weak.
They're weak, right? So the faster that something evaporates, the weaker the attractive forces are. So non-polar molecules, if they're big enough, they can be liquids, like octane, gasoline, okay? It's a liquid at room temperature, but we know that gasoline evaporates pretty quickly if you spill it on your driveway or something, right? So all of your fingernail polish remover and all your organic things that are non-polar, that are liquids, they tend to evaporate very quickly, okay? And so then the last thing, increase in strength. And what did we say, Anna, with what?
Bigger molecules.
The size of the electron cloud. Okay, so those are all the important things to know about LDFs. All right, so we can take a pause. Go ahead and stop that.